Hey guys, and welcome back to another video. This video marks the final video in our Precalculus series here on our channel SG Quantify. So without further ado, let's get right into it. Alright, so the topic of this video is 3.8 polar coordinates. Okay, so let's begin with the coordinate plane. Alright, so suppose I have some point in the coordinate plane and I'll call it xy, right? So we can also graph the circle that intersects this point and goes to the origin, right? And so then this length right here, this is the radius of the circle, right? So we'll call that r. And then we can also consider this angle right here, which we'll call theta, okay? So now we can actually represent this point xy using r and theta. And so that's exactly what polar coordinates is, right? So polar coordinates is simply expressing a point as r theta, where r is the radius of the circle, so like the distance from the origin to that point, and then theta is the angle that the point that ray makes with the positive x-axis. Okay. All right. So now let's see how we go from rectangular coordinates, which is what this is. So x comma y, that's called rectangular coordinates. So let's see how we go from rectangular coordinates to polar coordinates, and then the other way around. So to go from rectangular to polar coordinates, we need to be able to find r using x and y, and then we need to be able to find theta using x and y. So to find r, that's pretty easy, right? Because we could just draw the following triangle, and then realize that this side length right here is x, and then this side length right here is y, and then we can simply just apply Pythagorean theorem to find r, right? So then applying Pythagorean theorem, you get r is equal to the square root of x squared plus y squared. Okay. And so then to find the angle theta using just x and y, we can consider tangent of theta, because tangent of theta is equal to y over x, because tangent is opposite over adjacent, so y over x. And the reason that we only want to be able to define these in terms of x and y is because we're going from rectangular to polar, right? So in rectangular coordinates, we only know what x and y is, right? We don't know what anything else is. So that's why it's really important that we are able to find r and theta using just x and y, because that's the only thing that we are given when we are in polar coordinates. Okay. And another thing I want to mention is that to find theta, you have to take inverse tangent of both sides. But the domain, like the range for inverse tangent, is the fourth quadrant and the first quadrant, right? So you might get a negative angle, and that's not possible though. So that's why always make sure that you add like pi to your angle so that you can make it positive. Okay. But anyway, that's going from rectangular coordinates to polar coordinates. Now let's see how to go the other way around, namely polar to rectangular. So for this one, we can consider some basic trigonometry. Okay. So now we want to be able to express x and y in terms of r and theta, right? Because we know what r and theta is because we're in polar coordinates, and we want to convert them to rectangular coordinates. So if we consider cosine of theta, cosine is adjacent over hypotenuse. So this is adjacent side is x, and then the hypotenuse is r. So cosine theta is equal to x over r. And then multiply both sides by r, so you get that x is equal to r cosine theta. Okay, so that's how you find the x value. And then similarly for y, we can consider sine of theta. And then remember that sine is opposite over hypotenuse, so that's y over r in this case. And then again, multiply both sides by r, so you get that y is equal to r sine theta. Okay, so yeah, that's how you convert from polar to rectangular. All right, so now that we know that, we can do some practice. All right, example 1. So we're going to convert the following. So let's say we have the following point, and this is rectangular coordinates, right? So we want to convert this to polar. So we're going from rectangular to polar, right? So we know what x is, x is equal to 3, and we know what y is. Y is equal to 4. So what equations can we use to find r and theta? Well, to find r, we can use the Pythagorean theorem, right? Square root of x squared plus y squared. So then we can substitute in. You get 3 squared plus 4 squared, and that's equal to 5. So r is equal to 5. And then to find theta, recall that tangent of theta is equal to y over x. So that's equal to 4 over 3 in this case. So then theta is equal to the inverse tangent of 4 over 3. And for our purposes, we're going to be in radians. Okay, so then theta is approximately 0.927 radians. And I'll just include that at the end, but you don't really have to. Okay, so then this 0.34 in polar coordinates is 5 and then 0.927. Okay, nice. Let's do another example. All right, so now let's go the other way. So now, given a polar coordinate, let's convert this to rectangular coordinates. All right, so from here, we can see that our r is equal to 2 and theta is equal to pi over 3. So we want to go from polar to rectangular, right? So remember that x is equal to r cosine theta, and then y is equal to r sine theta. So here we have 2 cosine of pi over 3, and then we get 2 sine pi over 3. So then we can recall our exact values. Cosine of pi over 3 is 1/2. And so then 2 times a half is just 1. So x is equal to 1. And then sine of pi over 3 from exact values is square root of 3 over 2. And so then this just becomes square root of 3. Okay. So rewriting this in rectangular coordinates, we get 1 comma root 3. Okay. All right, nice. So now let's move on to representing complex numbers as polar coordinates. All right. So now we want to write complex numbers as polar coordinates. So let's consider the complex plane. So namely, the vertical axis is the imaginary axis, and the horizontal axis is the real axis. Okay, so basically what this means is like if you have some point like a plus bi, so let's say we had like some complex number z is equal to a plus bi, right? So then the real part of z is equal to a, and the imaginary part of z is equal to b. So this is a common point of confusion, right? Because some people may think that the imaginary part of z is bi, but that's incorrect, right? The imaginary part of z is simply just the coefficient of I. So it's just b. And so then on the real axis, you graph the real part of z, and on the imaginary axis, you graph the imaginary part of z. So if this point right here, like a, and this is like right here, b, then this point right here would be z, right? So that's z right there. All right. But like this is almost like analogous to like rectangular form and like just like the real plane, right? So that's why we can also just rewrite this or like express it in polar form. So again, let's consider like the circle with radius r that goes to this point. So we'll call this length right here r, and then we'll call this angle right here theta. Okay. So again, we can like draw in this triangle right here, right triangle, and then we can do some trig, and then we can rewrite a plus bi in polar form. Right, so we know that this length right here is a, and then this length right here is b, just from the definition of like z, because it's equal to a plus bi. So, all right, and so then we can consider cosine of theta. That's equal to the opposite over hypotenuse, so that's b over r. So, or sorry, this is sine theta. Sine theta is equal to b over r, opposite over hypotenuse. So then b is equal to r sine theta. And then we can consider cosine theta, and that's equal to adjacent over hypotenuse, so that's a over r. And then that means that a is equal to r cosine theta. So then we can substitute in these values of a and b into the original equation for z. So we get that z is equal to a, which is r cosine theta, plus bi. So I'm going to factor the I out, and then we have b, which is r sine theta. So this right here is the polar form of a complex number. Okay, and you might be wondering, like, what was even the point of like doing this? Like, what's the motivation behind writing a complex number in polar form? Since because like it looks more complicated, right? But actually, writing complex numbers in polar form makes it easier to like take powers of complex numbers, and just like makes like doing arithmetic much more easier. All right, so that's like the one implication of like rewriting the complex number in this way. But anyway, let's do some examples converting complex numbers to polar form. All right, so let's suppose we have the following complex number, 5 plus 12i, right? And we want to convert this to polar form. So we know that our a value, a is equal to 5, and then b is equal to 12, right? So we know that r is equal to a squared plus b squared, right? And this, again, this just comes from like the Pythagorean theorem. And then as we will see, tangent of theta is equal to b over a. Again, that just comes from like tangent equal to opposite over adjacent, right? So this just can be derived like graphically. But substituting in, we get 5 squared plus 12 squared, square root of that, that's equal to 13. And then here, we get tangent theta is equal to 12 over 5. So then solving for theta, we get 1.176 radians. Okay, so then we can rewrite the z as, so it's r cosine theta plus I and then r sine theta. So we have 13 cosine of 1.176 plus I, so plus 13i sine of 1.176. Okay, and so then if you like simplify like 13 cosine of 1.176 and like 13 sine 1.176, you're just going to get the same number back, 5 plus 12i, right? So that's like kind of like defeats the whole purpose of converting. So that's why we just like leave it like this, right? But yeah, that's how you convert. All right, let's do another example. Okay, so again, we know that a is equal to 7 and b is equal to 24. So r is equal to the square root of a squared plus b squared. So that's equal to the square root of 7 squared plus 24 squared, which is equal to 25. And then tangent of theta is equal to b over a. So we get 24 over 7. So then take an inverse tangent, and then adjusting as necessary, we get 1.287 radians. So then we can rewrite this as, so it's r cosine theta, so that's 25 cosine of 1.287. And then we have 25i sine of 1.287. All right, so this is the polar form of 7 plus 24. All right, cool. All right, so then one last thing that we need to cover is polar graphs. Okay, so you might be wondering, like, you have like r comma theta, right? That's like a polar coordinate. But like you might be wondering, like, how do you even like graph that? Because like in the rectangular plane, you have grid lines. Like it's not that easy to like graph r values and like theta values, right? So that's why we have specialized graphs just to graph these called polar graphs. And basically, what they are is like instead of having grid lines, or like instead of having rectangular grid lines, we have circular grid lines. Like it looks something like this, right? And basically, what this is that each circle represents like one value for r. So, for example, this circle could be like radius 1, this one could be like radius 2, radius 3, radius 4, and like so on, right? So that way, if we need to graph like, so like that helps us graph like our values, and then you could just like use a protractor, and sometimes like the angles are built in, right? So like they might have like angles like as follows, so you can like graph, and this is like a really bad drawing, excuse myself, but they probably have like angle measures, so you can like graph at least like the well-known angles, so to speak. And so this helps us graph polar coordinates. So like as an example, let's say you wanted to graph like 2 pi over 6, right? So you would go onto, this is actually getting very messy, I'm going to redraw this. So right, so this is radius 1, this is radius 2. So you just go on the radius 2 circle, and so you know that your point lives somewhere on this circle, right? And then you start at your positive x-axis, and then you'd go up pi over 6 units. So it's probably like lives somewhere right there. So that point right there is 2 over pi over 6. Okay. But yeah, that's basically how you graph polar coordinates. Okay. But yeah, that pretty much concludes this lesson on polar coordinates. If you enjoyed and found this helpful, please make sure to leave a like and don't forget to subscribe. I'll see you guys in the next series.